Hello, this is Mathman, and this is the second video in a series that I'm making regarding trigonometry. And the first video dealt with the basic sine and cosine functions and how they are derived using a right triangle. We took a look at some of the properties of sines and cosines, periodicity. We looked at how all of the trigonometric functions were derived from the basic sine and cosine function. And we also looked at how to convert from degrees to radians. Now, in the second video, we're going to take a look at two identities. We're going to look at the double angle formula, how that's derived, and we're going to look at the law of sines. Now, we're going to look at the law of sines first because it's easier to derive. And then the double angle formula then falls out of the law of sines. And again, it's just the application of the basic definition of a sine function that we'll be applying throughout. And we'll go through the methodology step by step. And we won't try to cover too much territory in this video, but we're going to show you how it's derived. Most teachers, math teachers in trigonometry, will just give you the double angle formula and leave it at that. You just have to memorize it. The double angle formula basically is the sine of the angle plus another angle is equal to sine of one angle times the cosine of the other plus the sine of the cosine of the remaining. So that is typically, we'll just leave it like that. I think you can see it better that way. Try to get the camera aimed in a good direction. That is a double angle formula, and usually it's just given, but we're going to derive it. So in order to do so, we first need the law of sines. And in doing that, we'll start out with a scalene triangle. Let's see, I need something to draw with. Should be good enough. Now you remember with the scalene triangle, the sides A, B, and and C are not equal. So we have the condition A is not equal to B is not equal to C. And similarly, the angles opposite are not equal. A is not equal, angle A is not equal to angle B is not equal to angle C. Now, the first thing we're going to do is drop a vertical, a perpendicular, and this perpendicular is going to be a right angle to the base, and it's going to be height h. So what we do here is we simply look at the law of sines. One thing we notice here is that this angle C is broken up into two angles. We're going to call them phi and theta. Okay, so angle C is equal to phi plus theta. Okay, now we go to H. Let's see, H over A is equal to this is the opposite of that angle, so that's the sine of B. Similarly, H over B is the sine of A. Now we have two functions in which we have H, so we have H equals A sine B, but H is also to B sine A. Simple. Now if we divide through by AB, we have sine B over B is equal to sine A over A. That's only part of it. Now we have to work on this side, the C, with angle C. So what we do here is we got a little room over here to work. We drop another perpendicular. And in this case, we drop it from this vertices down to the base. You're going to have to forgive my hand drawing because I'm not very good. That is, again, a right angle. We'll call this vertical Q. And now we have these subangles. They come into play. So, oops, I erased my side. Okay, so we have Q over, let's see, Q over A is equal to, now Q is the opposite of angle C. So that's the sine of C. We also have, that looks more like an infinity sign than Q. Q. We also have Q on C. Q on C is equal to the sine of A. See, Q is the opposite of A. Sine of A. So, now we have sine A Q equals a sine of C equals C sine of A. Now if we divide through by AC, we have sine of C divided by C equals sine of A divided by A. Well, we have sine of A over here, and that's equal to the sine of B. So we completed our law of sines. So sine C over C is equal to sine of B over B, the sine of A over A, and we've got our law of sines. Not very hard to derive. Now, this here is a very important and fundamental trigonometric identity. And you'll see it over and over and over again in trigonometry. Now, let's take a look at the double angle formula. We're going to take the advantage of this relationship. We're going to take a look at the sine of A, or let's say the sine of C over C is equal to sine of A over A. And the reason we do that is because we see that angle C is equal to phi plus theta. So we have sine phi plus theta equals, doing a little algebra, C on A, sine A. But if we remember what we looked at as a property of a right triangle, that theta, that A is equal to 90 minus theta, we have C on A sine of 90 minus theta, and that is equal to C on A cosine of theta. So we're making some progress here. Now, C on A, we're going to have to take a look at some other features. Now we have this vertices divides the base x and L, where x plus L equals C. So we add that there. We have x plus L on A cosine theta. But then we expand that out, and we have x on A cos theta plus L on A cos theta. Well, x on A is the sine of phi. So we already have one aspect. We have sine of phi cos theta plus L on A cos theta. Well, this is the term now that we have to deal with. So we're running out of board space, so we're going to have to rewrite our derivation here. Get a good look at this. Have a good long camera shot so you can see how we use the law of sines and some basic trigonometry, right triangle trigonometry, how to get to this last stage. So let's erase this, and we'll start with up here, sine of phi plus theta equals sine phi cos theta plus L on A cos theta. Okay, so now we've got that. We have a little room to work with. Now, it's the L on A that we're interested in. Now, we can take a look at H on L, and we see that H on L is equal to the tangent of A. We also know that H on A is equal to, H on A is the cosine of phi. See, adjacent over the hypotenuse is the cosine of phi. So we have cosine of phi. Now, to get L on A, we just take the ratio of those two. So H on A on L, let's see, let's do it this way. H equals L tangent A, and that equals to A cosine phi. So if we go h on tan A equals L, and h on cosine phi equals A, we have L on A equal to h tangent A on h cosine phi. But that's basically, these cross out, cosine phi on tangent A. So now we have a ratio for L on A. So we can write that's equal to sine of phi cosine theta plus cosine phi on tangent A cosine theta. Let's be correct. All right, so now we have to figure out what tangent A is. Well, again, we use the A is equal, whoops, that looks like a 9. A equals 90 minus theta. So tangent A equals sine A over cosine A is equal to cosine theta over sine theta. And that's what the tangent A is. So we have now sine phi cosine theta plus cosine phi cosine theta on cosine theta on sine theta, so that comes up in the numerator. These two cross out, and we've proven the double angle formula. So we have sine phi cosine theta plus sine theta cosine phi. And this is sine theta phi plus theta. And we have proven it. This is the derivation for the double angle formula using the law of sines and some fundamental trigonometric properties. And this is one of the most important identities, trigonometric identities, that you'll find, and this is how it's derived. So right now that's a lot to digest, and I think we'll leave it at that. And so we'll conclude our video at this point. I hope you enjoyed it, and I hope that you found this instructive. And generally speaking, I hate it when people just give you formulas to memorize. You can take the very basic fundamental relationships like sine and cosine, and you can work out. That's the beauty. This is one of the most beautiful things in trigonometry, is how you can use the most fundamental relationships to derive some very profound results. And in just 15-20 minutes we derive the law of sines, and we also derive the double angle formula from the law of sines. And I hope that it's clear. The methodology, the approach I used was with a scalene triangle, and the key to it is dropping perpendicular vertices, or from the vertices perpendicular lines to the base, to the opposite base, and using right triangle trigonometry and recognizing that certain aspects like this relationship apply. And you can go from here right directly to this beautiful result. So this is Mathman here, wishing you the best, and we'll take a look at trigonometric functions in much greater detail, but I think right now this is a pretty good point to stop, and I wish you all well. Until next time, so long.